This is a demonstration of a CAN driver implemented using the PIO coprocessors on the RP2040. The experimental setup is pictured here. You can see 4 Raspberry Pi Picos, each of which has an RP2040, and each of which communicates to its own CAN transceiver. So I'll show a labeled picture here. You can see the CAN transceiver that communicates with RP2040 number 1 and number 2 in the center top of the breadboard. And then the CAN transceivers in the center bottom are on a vertically oriented breakout board. So they're difficult to see at this angle, but I'll show another picture. In short, each RP2040 communicates with its own CAN transceiver, and then every transceiver is hooked up to the CAN bus, which is there in the middle of the breadboard. This is a more obliquely angled photo of the same setup where you can see the two CAN transceivers 3 and 4 down at the bottom of the breadboard on that vertically oriented breakout board. And the experiment that I'm about to demonstrate is illustrated here. Each RP2040 is assigned a different arbitration number for the CAN transactions, and each communicates 1,000,000 packets in a clockwise direction. So RP2040 number 1 communicates to RP2040 number 2 in the upper right corner. Number 2 communicates to number 3 communicates to number 4, and number 4 communicates back to number 1. Furthermore, the arbitration numbers of each of these RP2040s is such that number 1 has the highest priority arbitration number, followed by number 2, followed by number 3, and then number 4 is the lowest priority. So what we'll expect when this experiment runs is that each RP2040 will attempt to send 1,000,000 packets as quickly as it can, but every time there's an arbitration conflict, RP2040 number 1 will win all conflicts, number 2 will win all conflicts except those with number 1, number 3 will win those against number 4 but not against 1 and 2, and number 4 will lose all arbitration conflicts. The consequence of this will be that we should expect that RP2040 number 1 finishes transmitting its packets first, followed by number 2, followed by number 3, followed by number 4. And in this particular experiment, the system is configured such that there's a baud rate of 1 megabit per second within each packet. That's configurable. I could change that. And furthermore, each packet contains fully randomized data. So each RP2040 generates a random payload and sends it, and then once that payload is sent, it'll generate a new random payload and send that next one. And there's 500 microseconds of idle time between packets. So I'm going to show the beginning of the experiment. I boot up each of the RP2040s, and they'll each start communicating data as quickly as they can. And what you'll notice is that the number of sent packets indicated in the upper left terminal window matches the received packets in the upper right, and that's because RP2040 number 1 in the upper left is communicating to number 2 in the upper right. And you can follow that pattern the whole way around. This is illustrating the bus traffic on the oscilloscope. So you can see 500 microseconds of separation between packets and a 1 megabit per second baud rate within each packet. And then what we'll expect is that number 1 finishes first in the upper left. So number 1 is indicating that it sent 1,000,000 packets. Number 2 indicates that it received 1,000,000 packets. Number 2 has just finished. Number 3 has just finished. And now the lowest priority node has finished. And you can see that each node has sent 1,000,000 packets, each node has received 1,000,000 packets, and each node has rejected 3,000,000 packets, which makes sense because each node rejects its own packets.